Swayam Prabha. Digital India. Educated India.
So, starting from interval graphs, so we were considering some generalizations, for instance circular or graphs in the last class, okay, none of the classes. So, now I will tell you about some other things, which is parameter which comes from the attempts to generalize interval graphs further to higher dimensions. So, interval graphs are like in the intersection graphs of intervals on the real line, something like this. So, what should be the corresponding thing in 2 dimension? So, in 2 dimension, the intervals correspond to rectangles, but axis parallel rectangles. So, because both in the x direction and y direction pick an interval and then that is the rectangle. So, essentially the Cartesian product of 2 intervals. So, in the x axis you find a interval say a comma b, and in the y axis you can find a interval c comma d, then this become AC, right, BC and AD BD, right. So, this will be the rectangle. So, that is why axis parallel rectangles. So, it is actually going from the intervals by taking Cartesian product of intervals on both the axes. Now, we can define an intersection graph on these objects, namely the intersection graph of axis parallel rectangles. You are given a collection of axis parallel rectangles, and then for each given axis parallel rectangle on 2 dimension, you have to associate a vertex, and then 2 vertices are made adjacent if the corresponding rectangles intersect. This is sometimes called a rectangle intersection graph or sometimes rectangle graph. Like fleet maintenance problem, I think, so when this military application, I guess so. So, the they say, so each ship can be placed, so maybe you can say parked in on a rectangle. So, rectangular area is given, right, okay, this place you can place a ship, right, and then so several such possible positions are given. So, now something here you can place, here you can place, somehow due to some reason you are not allowed to place your ship on other places, like only on one of these rectangles here. So, at the same time, how many ships can you park? Can be there, because if you can see that there is this rectangle structure here, some rectangles are intersecting, and whenever rectangles are intersecting you put an edge between the corresponding vertices, right. And then what is the, if I ask how many ships can be placed simultaneously, what is the corresponding parameter on the graph you construct? So, the predefined rectangles are there, rectangular positions, places are there where you are allowed to keep your ship when it is not moving, right. So, you come back from somewhere, you have to place in one of these places, maybe you have put some four flags and all to denote that place, right, I do not know. So, maybe some lights or something like that, you have to place it, and then several such rectangles are identified, and based on these rectangles you can construct the conflict graph, the intersection graph, namely whenever 2 rectangles intersect the corresponding vertices will have edge, which means that if you are placing a ship on a certain rectangle, then adjacent, so the rectangles which intersect with that cannot be used, right, because it may hit or something like that, right, because that is why the rectangles are when they are intersecting, you are not supposed to place 2 ships in those rectangles. So now the question is, how many ships can be placed at the same time? What is that parameter? Maximum? It is independent set. So this is the finding the independence set question here. So I just tell you that this kind of questions, like the graph parameters, will translate to some questions like this, right? How much, how many can be placed and things like that, right? Okay, so this rectangle graphs is in 2 dimensions, and now there can be a similar intersection graph in 3 dimension also, right? So what will be that? So instead of axis parallel rectangles, you will consider axis parallel 3 dimensional boxes, right? Axis parallel 3 dimensional boxes, hyper rectangles or something like that, you can say. So 3 dimensional boxes, box is a nice word. And then whenever so many such boxes are given, and then whenever, so corresponding to each box you have to introduce a vertex, and whenever 2 boxes intersect, you should place an edge between them. This is the intersection graph. So you can go to higher and higher dimensions and define this kind of intersection graphs. And you can see that if a graph is an interval graph, it is also a rectangle intersection graph, right? It's easy to see, right? Because 1 dimension can, you just have to put a dummy 2 dimensions, some little height you have to give those intervals, right? It does not harm. Similarly, if you have a rectangle graph, you can make it 3 dimensional boxes also, right? You just, for each rectangle you give a little height and then make like boxes, right? The heights, right, essentially what is intersecting is the rectangle, so what you can always give. So therefore going upward is, the downward is not correct. For instance, if something is intersection graph of 3 dimensional rectangles, it does not mean that it is intersection graph of 2 dimensional rectangles, or the other way. So even smaller thing, like if it is the intersection graph of 2 dimensional rectangles, axis parallel rectangles on the plane, it does not mean that it's an interval graph. Can you give me an example? Quick example.
2 boxes, 1 above.
2 boxes.
1 above.
2 boxes, 1 above the other, like this. But this is only a, yeah, if you project it, but you can always get the same graph structure, right? So the saying that given a graph, okay, maybe I should have asked it more properly. So the question is this thing. So if given a graph, so like we asked in the case of interval graphs, given a graph, do we have a representation using intervals on the real line such that the given graph is the intersection graph of those intervals? Same way we can ask this question, namely given a graph, do we have a representation using the axis parallel rectangles, right? As the intersection graph of axis parallel rectangles on the 2 dimensions. Similarly, given a graph, do we have a representation? Right. So what I was telling, that if a graph has a representation in 2 dimensions, then it has a representation in 3 dimensions also. If it has a representation in I dimension, then it has a representation I plus or more dimension also. Not the other way. For I asked you to give an example, where a 2-dimensional representation is possible, but a 1-dimensional representation is not possible. This is not correct, because this corresponds to this single edge graph, right? This can, okay, in the real line also you can get it, right? So, but what you cannot get, you know, for instance, if I draw something like this, right? What is this? What is the graph corresponding to this? It's a cycle. It's a cycle on how many vertices? See, 1, 2, 3, 4, 5, like this, right? we know that this cannot be an interval graph, or 4 cycles also cannot be an interval graph, right. So therefore, this cycles can easily be represented as the intersection graph of rectangles, but not the intersection graph of intervals on the real line, right. So when you go from 1 to 2, some power of the representation has gone up, it can capture more things, right. And similarly trees, we have seen that several trees cannot be, for instance this tree, like if this kind of a tree itself is not a interval graph, because we have seen that for the first star it should be something like this, and then when you want to put the other thing, you will find it difficult, right, because if you want to touch something with this thing, but then without touching the big line, it will be difficult. So but then if you go to the rectangle thing, it's very easy to represent all trees. How? So first for the root you will put a long thing, and then for its children you have to put something like this. Maybe how many ever children, you have to adjust the length. Suppose there are 3 children, you can put like this, right. And for the children of this one, you can put like this, right. 3, I am putting 3. If you have more, you just adjust the size of that, and like that, right. You just have to make it shorter and shorter. You can do whatever you want. A tree can naturally, but it's not an interval graph, right. So therefore some graphs are there which can be represented in 2 dimension, but not in 1 dimension. But the question is it possible that all are representable in 2 dimension? There is nothing which requires 3 dimension, or maybe in 3 dimension everything can be done, or when you go to 4th dimension then everything can be done. Is it possible? Or do we need higher and higher dimension? Are there some graphs which require more and more, which cannot be captured in lower dimensions, right? So it's difficult to just imagine, but it so happens that yes, there are some graphs which requires whichever dimension you tell. I can construct a graph which cannot be represented in that dimension or smaller, right? For instance, you tell me that you're giving me n dimensions, or say n minus 1 dimensions, right? I'll show you a graph which requires n dimensions, right? 1 extra is required. It's not that you cannot do. You cannot actually do it in this thing. How will you do that? So this is the construction. You take a complete graph on 2n vertices, and then remove a perfect matching from this. Take a complete graph on 2n vertices and remove a perfect matching from it. Because there are 2n vertices, you should be able to pair up now 1, 2, 3, 4, 5, 6, something like that. So it will look like this. So you are removing a perfect matching from like this. So you can draw it better. So this is n vertices, and this is n vertices. There are, because I had 2 n vertices in the thing, and then I have this corresponding thing. So this I can call 1, 2, 3, 4 like that n, and this is 1 dash, 2 dash, 3 dash, n dash, and then 1. See, the only thing which is missing is the missing edge is this one, this 2 to 2 dash, 3 to 3 dash, 4 to 4 dash, n to n dash. All other edges will be there. Okay. It's a different way of viewing it, that's all, right? Just you can remember that you had k to n and just removed one perfect matching from this. That is what this is. This has several names. When we work on these box representations. We call it Roberts graph because F.S. Roberts was the person who first wrote a paper with that name, box representations and cube representations, and he constructed this, he showed that this graph requires n dimension, but if many other people won't even like that idea of calling this as Roberts graph, because this is very famous and many people, yeah, this is K2n bar or something like that for some people, because this is a collection of edges, the complement of a collection of edges. Some people call it cocktail party graph. In some algebraic graph theory books and all, said cocktail graph, party graph. I guess it is like you go, 2n people go to a party, n of them are women, and okay, actually they are husband wife pair, and then when they go to the party, what they do is they talk to everybody else other than their wife or husband, right? So therefore this is the graph for that. So cocktail, I don't know why it's cocktail. So so there are several names for that, but I stick to the name Roberts graph. So F.S. Roberts had written a textbook on combinatorics, I think quite early, and then yeah, he has worked on several problems which has some connection with applications. So in combinatorial questions which can be translated to some questions which has some application. This also he did something like that because he thought that it has some relation with some ecology problems in ecological niches and things like that. Ecological niche. So it's it comes in various places because it can be like some of the study of the evolution, like millions of years ago, what kind of species happened over there, and then there are people who want to figure out what kind of species coexisted, and these are all difficult things to do. So they try to do it. So there are various models. They say if they preyed on this, two predators preyed on the same prey, then they might have coexisted and things like that. But one model is this thing. So to each species you associate a box and say that it is the niche for that. That box will capture the species. Why? Because it's like this. So if you are a human being species, so you can exist in a certain temperature range only. I don't know what is the smallest, maybe minus 40 to plus 80 or so, sounds okay, plus 70 is fine. So something like that. Beyond that, anyway, it's sure that the species will not exist, right? I don't know whether you can go to that range, but let's say extreme, right? You cannot go below that. It's very difficult to exist. So there will be a certain temperature range in which. So in the temperature axis, you can mark that range for the what? That species, because if it existed, the temperature should have been in that range, and then pressure range will be there like that, the humidity range. So the people who study these things, so they will be interested in how many such natural parameters are required to study this interconnection network of species and all, right? Because that's what is the minimum dimension in which you can actually capture the interconnection networks and things like that. So there is some among those people, these are empirical, not mathematics, but they believe that not many parameters are required to understand these networks and all, right? These interconnection networks and things like that. So I haven't understood completely why all these things, this kind of empirical thing is, but that's maybe by observing data and studying it, they believe like that. And then there is this model is like, now can you see that temperature axis, whatever interval you put, and pressure axis you have put an interval, you take the cross product of all these things, you will get a box in space, right? In higher dimensional space. This box corresponds to that species. Abstractly, the species is that box now, right? Species exists somewhere inside that box, right? We can think like that. Or the conditions, the corresponding to the time it existed should correspond to some points in the box. Now, if another species coexisted with it, then that means two boxes should intersect, right? So if a mammoth and human beings coexisted at some point of time, the box of the human beings should could intersect somewhere in the right with the box of that. Otherwise, how can it coexist? Temperature is different, pressure is different. You should agree on all the parameters, right? Then only you could have coexisted. So you can make this possibility interconnection networks and all that's used by and along with this predator prey model, you can make some inferences and things like that. Beyond that, I don't know how you do that and what kind of how solid will be the results and things like that. That I have no idea because. But then there are such studies, and like many such things can be done. For instance, in suppose in a political voting situation or something like that, you can suppose if you are a voter, right, your opinions, political opinion with respect to each idea. So if you are like what about in US and all says social security should be given to everybody or should not be given. So there should be extreme left to extreme right opinion, right? So you think that yes, everybody should be given freely without thinking. Some people say that, oh, if they know, why are you giving free money to people, right? That's the other extreme. So for every political opinion, there, if you plot it on a line, probably you can get an interval in which a particular person's opinion is. Not that you just say that no, it should be like this. That's not possible, right? I am happy with some range of this thing, right? My opinion can be. So for each each political issue, you may have an opinion which may be plotted on a line, right? Then you can mark your okay, this is my range in which things are acceptable to me. Beyond this thing, I think it's not okay. If a candidate is saying that my opinion is beyond, I won't vote for him, right? So like that, you can imagine that, and then you will become the voter will become a box. Right, because when you take the Cartesian product of all these opinions from each of these axes, you will become a box. Then two voters will have different boxes, but still they may intersect, right? Even if in one political issue they don't have any intersecting area in their range, then the boxes won't intersect, right? So where will you place? Suppose you are a candidate, politician, and politician being politician, he can change his opinions, right? So it's not that you have a fixed opinion, and if you want to win, you have to change your opinion according to the voters thing, right? So therefore, what you will look at is how many people I can get, right? So that means you have to place yourself at some point which is in the intersection of so many boxes, right? So in the maximum clique is what it is, right? Isn't it? So, but I just made you aware of the possibilities of these boxes and this intersection represent. Though it will look like fancy initially, but yes, but see, things will be empirical when you study this thing. It's not that we will get perfect answers for things or something. This is just for studying modeling and sociologists and all. We'll be looking at economic theory or something like that, but you will get some information from this thing, mathematical models to study something. So I give you a glimpse of what it corresponds to. The rest is up to your imagination. You can see how you can use it. And then this is the intersection graph of boxes. Now I'll show you how the box this cocktail graph, Robert's graph requires high dimension. Right? So this is like nice mathematics which teachers can pose in a like competitive examination or something like that for beginning students. So now I want to show that before this we will but to do this thing we will have to show how we can connect the box representation and interval graphs very mathematically. Until now I was telling from interval graph how the box representation comes, because the intervals are on the axes, and then Cartesian product corresponding to each vertex we have an interval on each axis, right? Because there are several interval graphs you are seeing on different axes, right? Because the temperature axis you have the temperature intervals for forming some interval graph. So in the pressure axis there was another interval graph, but each interval correspond to a vertex, right? There also there is an interval, in the y axis also there is an interval, like that. So but then you can say that if you get k interval graph, k interval graphs drawn on k different axes, then we have the intersection graph of k dimensional boxes, right, because each vertex will become a box in k dimensional space, because the Cartesian product of the intervals associated to each vertex and each axis will take the product and you will get k dimensional box. And the converse is also true. Suppose you have a k dimensional box representation, then what you could do, like somebody was trying to point out here, you could have taken the projection to each different axis, k different axis, because k dimensional you can have k axis, and then k different axis you could have taken the projections. When you take projections, what you get is an interval graph on the same set of vertices, corresponding to the box intersections. Each box is corresponding to a vertex. Now, when you take a project to the x axis, one box becomes one interval. So, therefore, there is an interval graph on the same set of vertices, right. So, one interval graph will come on the x axis, one interval graph will come on the y axis, and one on the z axis. On each of the axis, k axis you will get. So, you will naturally get k interval graphs. The question now is, suppose I make these interval graphs, not necessarily the picture, just the graph, right, and then and keep the graph somewhere, and for x axis whatever I got I kept, and y axis whatever I got I kept. These are all interval graphs now, not necessarily the representations. But and then I deleted all the pictures, right, even the first graph I forgot where I got this interval graph. Can you recreate the original graph? That is the question. Original graph alone, even without going these pictures. Yes, because the set of vertices is same everywhere, right. Now, what you should do is, you could have again drawn this this thing, and then we could have got back the k interval box representation, but what I am telling is, even without drawing you can get back. Why? Because the vertex set is same. Now, you know that when suppose some information, you may think that when you take the projection some information may be lost. So, suppose two boxes are intersecting here. When I take the projections, they are intersecting now, therefore, the edge between this and this is there here and here also. But then sometimes an edge may appear when there is actually no edge. How? For instance, suppose there was one box here which is not intersecting with this, right, but still when you take the projection, it will come somewhere here, it is intersecting here. So, the extra edges come. So, that means what you get, the interval graph you get by taking a projection is on the same set of vertices, but the edges may go up. If there was an edge before, that edge will be there. So how will you take care of the situation? So, do you think that I have lost the information completely? No, actually that is stored in the other place, right. Suppose if you look at here it will be clear, right, because this projection will be here and then this projection will be here if they are not intersecting, right. In other words, if two boxes were not intersecting, it is possible that in some of the axes you may see the edge unnecessarily, the absent things may become present, but there will be at least one axis where it is still not intersecting, and therefore, it will be absent, right. So, the point is that this corresponds to the box representation in the k dimensional correspond to k interval graphs. So, all the k interval graphs should be super graphs, that means the edges should be superset there, but if at all one edge is missing, then it should be missing in one of the interval graphs. That is all what we need, right, not that it should be missing everywhere, because when you take the intersection of all these edges, we can, so you just have to see where the edges, we will say that the edge which is present in the original graph is the edge which is present everywhere, and the edge which is absent in the original graph is the edge which is absent in at least one of the interval graphs you created. So, this model is same. So, though this is quite a geometric question, so you can translate it to interval graphs and then say that actually the dimension in which you are representing the minimum dimension in which you can represent. We call it boxicity, the minimum dimension in which you can represent. It's called the boxicity of the graph. It is essentially the minimum number of interval graphs I1, I2, say Ik, such that the intersection is equal to G. When I say intersection equal to G, the vertex set is assumed to be the same everywhere, but the edge, we are taking the intersection on the edge set. Actually, we should write I1 intersection E of Ik is equal to E of G is what we should write, right. So, if you get something like that, then it is that minimum K is the thing. So, what I have told to summarize, so that box representation you are seeing in K dimension